Yet there is another outcome. If the stellar remnant has a mass between 1.4 and 2.2 solar masses, it forms a neutron star. Gravity crushes atomic nuclei, producing ultra-dense neutron matter with exotic physical properties. For several reasons, neutron stars are very difficult to observe. First, they are extremely rare. On average, only one such object exists per 1,000 normal stars. Second, they are very compact and emit little optical light, making them invisible before X-ray telescopes were invented. Unsurprisingly, the first neutron star was only discovered 3,200 light-years from Earth, the constellation Carina, a distant past. Two red giants live out the last moments of their existence. Before our eyes, one of them enters a new stage of stellar evolution. The fuel in its core is almost exhausted, and the star begins to rapidly cool. The fragile balance between gravity and the fury of thermonuclear explosions is irreparably broken. Trillions of tons of stellar matter rush uncontrollably toward the core, restarting a runaway reaction of thermonuclear fusion deep within the star. A colossal explosion tears the star apart, leaving behind a superdense core, heated to unimaginable temperatures. The shock wave irreversibly alters the structure of stellar matter, completely destroying its atoms. They compress into ultra-dense matter, producing countless neutrinos. In place of the destroyed giant remains a tiny but extremely massive clump of matter. Around it, the outer shells of the dead star scatter as a vast cloud, forming a diffuse, gaseous nebula. At tremendous speed, they crash into another nearby red giant. This is how, in the wake of a grand catastrophe, extremely rare and unusual cosmic objects come into being: neutron stars. To date, only a few thousand such celestial bodies have been detected, a tiny number compared to ordinary stars. To understand why they are so rare, we need to study stellar evolution. According to modern concepts, the fate of any star is almost entirely determined by its mass. If it is less than 8 solar masses, then after several stages of life, it becomes a white dwarf. Billions of years later, it is expected to lose its residual energy and turn into a hypothetical black dwarf. Yet there is another outcome. If the stellar remnant has a mass between 1.4 and 2.2 solar masses, it forms a neutron star. Gravity crushes atomic nuclei, producing ultra-dense neutron matter with exotic physical properties. For several reasons, neutron stars are very difficult to observe. First, they are extremely rare. On average, only one such object exists per 1,000 normal stars. Second, they are very compact and emit little optical light, making them invisible before X-ray telescopes were invented. Unsurprisingly, the first neutron star was only discovered. Yet there is another outcome. If the stellar remnant has a mass between 1.4 and 2.2 solar masses, it forms a neutron star. Gravity crushes atomic nuclei, producing ultra-dense neutron matter with exotic physical properties. For several reasons, neutron stars are very difficult to observe. First, they are extremely rare. On average, only one such exists per 1,000 normal stars. Second, they are very compact and emit little optical light, making them invisible before X-ray telescopes were invented. Unsurprisingly, the first neutron star was only discovered in 1967, decades after their existence was predicted. This became possible thanks to a strange effect tied to conservation of angular momentum. Most neutron stars rotate extremely rapidly, and the interaction of their magnetic and electric fields produces intense bursts of radiation with perfect periodicity. Such objects are called pulsars, and they make up the majority of known neutron stars. Their pulses are easily detected by X-ray telescopes, even from thousands of light years away. Today, over 3,200 neutron stars have been discovered, about 90% of them solitary, with the rest in binary or multiple systems. Most often, their companions are red giants or main sequence stars, but in rare cases, their companions are red giants or main sequence stars. But in rare cases, the companion is another neutron star. This happens when two similar stars reach the end of their lives at nearly the same time, and the explosion of one triggers the collapse of the other. Losing energy during their transformations, the stellar remnants spiral closer together, increasing their orbital speeds to extreme values. This is how the remarkable system known as PSR J0737-3039 was formed. Located about 4,500 light-years from Earth, it is unique because the second pulsar is slightly smaller and slower, with a mass of 1.25 solar and a rotation period of 2.77 seconds. If we look closer, their sizes are minuscule by cosmic standards, just a few dozen kilometers across. Yet their masses are comparable to stars. This results in unimaginably high densities. To understand this, we must peer inside. Mathematical models and theories of neutron star structure reveal even what our eyes cannot see. The outermost layer is called the atmosphere, but for neutron stars, this differs greatly from the gas envelopes of planets like Venus or Earth. For both pulsars in this system, the atmosphere is only a few millimeters thick. In young, hot neutron stars, it can reach a few dozen centimeters, mostly hydrogen and helium, though heavier elements can appear. Beneath lies the outer crust, hundreds of meters thick. Gravity here is strong enough to distort matter's structure, but not enough to overcome electrostatic repulsion between protons and electrons. Particles intermingle but retain integrity. Multiple forces, gravity, magnetism, electrostatics, centrifugal inertia, keep the crust in constant stress. Occasionally, this stress erupts as starquakes, creating mountains just millimeters high and cracks centimeters wide. Under extreme gravity, in these pulsars, the outer core extends to the center. But in more massive neutron stars, scientists believe an inner core exists, possibly made of exotic matter, quark matter, hyperons, or kaons. These remain theoretical. Looking at the system as a whole, we notice that the pulsars orbit each other at an average distance of only 800,000 kilometers, less than twice the Sun's diameter. Their orbital speed exceeds 300 kilometers per second, completing one orbit every 2.45 hours. Such motion causes relativistic effects. Another effect is gravitational redshift during eclipses. The nearer pulsar's gravity stretches the light from the farther one. Their periastron shifts dramatically by 17 degrees per year, making this the strongest known case of relativistic orbital precession. Could planets exist here? It's unlikely, but not impossible. Some worlds may have survived the dual supernovae, others formed later, but none would be habitable. Lethal radiation and extreme cold prevail. Observations show this binary pulsar constantly emits gravitational waves, shrinking the orbit by 7 millimeters daily. In about 85 million years, they will merge into. The merger will shine as one of the brightest stars in Earth's sky for a brief time. But eventually, even that echo will fade into the infinity of the universe. Friends, recently new films on the channel have been coming out less often than we'd all like. That's because they require hard, time-consuming work by many people. We put in more and more effort to create the highest quality and most informative videos. Your support is what keeps this channel moving forward. So if you enjoyed this, let us know in the comments and give us a like. New educational episodes are on the way.